In this video, we'll take a deeper look at the binomial distribution and how it relates to the normal distribution. Lots of things are binomial settings. We know that we often look at outcomes and say whether they were successful or not. The problem comes when we start to do sampling. When we sample, we usually do not do that without replacement, which means it's not truly independent because we're slightly changing the probability of success after we remove a person from our sampling pool. Now, it turns out that if our sample is small enough compared to our population being much larger, the difference in these probabilities is so small that it ends up not making a difference. So we do have a rule for this. As long as our sample size is less than or equal to 1/10 of the size of the population, that slight change in probabilities for each trial is so small that it goes out many decimal points, and by the time we round off our answer at the end, it's not something we would even notice. So we can use this formula where the lowercase n is our sample size and the capital N is our population size, and as long as we're taking a sample less than 10% of the population, it's good enough that we can still use the binomial distribution. Now, another thing that's interesting is that if our sample size gets bigger and bigger, that our distribution starts to look more normal. So here's what I mean. Here's an example where I took a sample size of 10, and you can see that it is slightly skewed to the left. If I increase that sample size to 20 and then to 50, you can see that it gets less and less skewed and it becomes more and more normal. So it turns out that if the sample size is big enough, I can use a normal distribution to approximate the binomial distribution. Now, this is nice because we have that nice packet of formulas with the table A on there with the z-scores, and we can use this whenever we have at least 10 successes and at least 10 failures. So we would calculate that by doing the number of trials times the probability of success, n times p, and as long as that's greater than or equal to 10, along with the number of failures, so the number of trials times the probability of failure, as long as that's also greater than or equal to 10, then we can use our normal distribution. Let's take a look at an example where these two new rules would come into play. So here we have a survey where we ask 500 teenagers whether or not they have a debit card. And it turns out that exactly 12% of them said that they do. So we want to look at X being the number of teens in a random sample of those 500 that have a credit card. First, we want to check whether or not this is actually binomial. So we're going to look for our BINS requirements. It is binary. They either have a debit card or not. There is a set number of trials, because I'm going to choose 500 teens every time. The probability remains the same if I'm assuming that that population has a 12% success rate. However, I'm picking 500 different teenagers. I'm not placing them back in the pool, which means that it's not technically independent. However, 500 is less than 10% of all teens. That means that it's going to be close enough to independent that I can move forward and use the binomial setup. So if we want to estimate the chance that 50 or fewer of them have debit cards, we're going to use our binomial CDF on our calculator, where we have a sample size of 500, a chance of success of 12% or 0.12, and we wanted to find out the odds or the chances that 50 or fewer of them have the debit card. That works out to about 9%. Now, let's see, first of all, whether or not I can use a normal distribution and then how that works out if it does. So, If I am guaranteed to have at least 10 successes and at least 10 failures, that means that I can use the normal distribution to approximate my solution. So the probability of success is 12%. That means I'd expect about 60 successes, and that is greater than or equal to 10. And if the probability of success is 12%, then 1 minus 12% is 88%. So 500 times 88% is 440, which is greater than or equal to 10. So I can use the normal distribution. So if I wanted to do that, I would use normal CDF. And I want 50 or fewer teens. So remember, if we don't have a lower bound, we use the negative 9,999 up to 50. And then our mean would be 60. And our standard deviation works out to be about 7.27-ish. So if we do our normal CDF, that works out to be about 8%. So it's not exactly the 9% that we got with the binomial, but it is an approximation, and 1% isn't a ton to be off by.